Welcome to this unit, Control Systems Engineering 1, which is offered in the School of Engineering, Energy and Built Environment, Department of Electrical and Electronics Engineering. My name is Engineer Alice Casera. Now the course content, I'll take you briefly through the course content, which takes 42 hours, equivalent to 3 credit hours. And before you do this unit, it is advisory that you do Electric Circuit Theory 2, Engineering Mathematics 2, and Calculus for Engineers 2. These are recommended because you will apply the calculus and all the electric circuit theory and the mathematics. You will apply them as we proceed. Now the purpose of this unit, that is the control systems, is to enable the learner to understand the classification, mathematical modeling, disturbance response, time domain, and stability analysis of control systems. So by the end of the course, you are expected to 1. Classify and describe the various control systems, carry out mathematical modeling and time domain analysis of control systems, determine the stability of a given system using Routh-Lewis criterion. Now the main course content is divided into 6 major topics. One is the classification of control systems, whereby you'll cover open loop and closed loop, linear and nonlinear, continuous and discrete. Then the second topic is the transfer function and mathematical modeling. The third topic is dynamic models and dynamic response. The fourth topic is the block diagram and signal flow diagram. Second last is time domain analysis of control systems. Then you'll have lastly the stability analysis. Remember, the main objective is how to obtain the stability of a system, so you'll have to cover mostly the stability analysis. So here you'll have assessment. End of the semester you'll do an exam of 70% out of 70. The CATS assessment will be out of 30, which incorporates 10% the CATS, that is the continuous assessment tests. 5% will be assignments and 15 practicals. So the textbooks and the recommended textbooks are also given there. However, you can also do further reading on other textbooks that entails the control systems. So to begin with lesson 1, that is the classification of control systems, we'll do a bit of introduction so that we come into terms with the control systems and all that. To begin with, control is the measuring the value of the controlled variable. Variable is our output of a system, and applying accordingly the manipulated variable, that is the input, to make the two as equal as necessary. So here we have input and output, and when you have input and output, you must ensure that they are as close as one another. So whatever does that is the control element. It compares the input and the output so that the two are as close as another. Another word or another definition of control means to regulate, direct, or command a system so that the desired objective is obtained. Remember, our main objective is to get an accurate output as possible. So it is the work of the control to regulate, direct, or command. The control word is something which is used in our daily lives. So it's only that the direct meaning is what is missing, but you usually use it. So we also have a system, which is a combination of systems that are a combination of components that act together and perform a certain objectives. So our main objective is still to get the output, the desired output, So we also apply subsystems, which is also combination of components. They act together. They must act together. If you find they are not communicating to one another, then there will be a very big error. So we can have a system which has maybe subsystems 1, 2, and 3 for us to get the output. So they must be linked. They must communicate. If there is a disconnect, then definitely you will not get your output. So those are the systems. And subsystems or systems is just one. When you have one system, then you can have some subsystems inside the system. So subsystem is any system that helps controlling the output of the control system. It is a combination of an arrangement of different physical components which act together as an entire unit to achieve certain objective. So remember, when you are doing any measurement or any control, you have an objective of which you want to derive at. So you must have your control here. You must have your system, if your system is one, or you must have subsystems. So you can find a control system having only control and system. It doesn't have the subsystem. Just depending on the type of measurement or the type of control you are trying to apply and the type of instruments that are involved. So for example, we have a classroom is a physical system, is a room along with the combination of benches, blackboards, fans, lighting arrangements, all that, and can be called as a classroom, which acts as elementary system. So classroom is just a system, but now the subsystems that are involved in that classroom, it includes the benches, lighting, all that, blackboards, etc. So we can say that is examples of the systems or subsystems. Another example, the same classroom, we have a lecturer delivering a lecture. Then it becomes a control system as the lecturer tries to regulate or command, direct the students in order to achieve the objective. My main objective as a lecturer is to ensure that at the end of the course, you understand everything and you get good grades. So I am trying to control you. By controlling, I command, do ABCD, I direct, and I also regulate. Regulation here means I try to ensure that you come to class early. I also direct you and command you, give you some exercises to be done and all that. So I'm trying to, that is a complete control system. Now when you talk of a control system now, we have a combination of control and the systems. Now we give a definition of, it consists of a subsystems and plants assembled for the purpose of controlling the outputs of the plants. Another definition is that it is a collection of components that is designed to drive a given system or plant with a given input to a desired output. But now the simplest definition of a control system, which you can never forget, is that it is an arrangement of different physical elements connected in such a manner to regulate, direct, or command itself to achieve certain objective. So these terms, command, direct, and regulate. So you are trying to command, the control is trying to command, direct, or regulate these systems or subsystems. So that is the simplest definition of the control system. Now when we come to the control systems engineering, that is the main unit. This is the engineering discipline that applies control theory to design systems with desired behavior. So when you put in the engineering terms, you must come with the design. How you should know how to design the systems. Remember, it is part of one of the objectives. Now we'll see at the elements of a control system. Just as a system, it must have different elements depending on the type of the system or the nature of the control you are trying to do. So we'll have the input, output, we have the plant, process, systems, subsystems. We have subsystems, or you can just say systems. Then we have the controller. So all these are there. And we can also have a disturbance, because in each and every environment there must be a disturbance. We call it noise. So depending on whatever system you are working on, it can have all these. It can have these put together. It can also have subsystems to give systems, or it can also have one. So whatever we are trying to explain is just how the input, output, subsystem, plant, process, all those, the function. So for example, the input is the desired response of a control system. It is the applied signal or an excitation signal applied to a control system from an external energy source. And output is now the actual response of a control system. When you input a signal, you expect to get an output. So output is the actual response of the control system. It is the signal of interest or the actual response obtained from a control system when input is applied to it. I've explained that. So subsystem is any system that helps controlling the output of the control system. Plant is the portion of a system which is to be controlled or regulated. Process is any operation to be controlled. We can have chemical process, economic process, biological process, and all that. Then disturbance is any undesirable and unavoidable signals beyond one's control. When you are trying to make some control in your system, then all of a sudden a disturbance occurs. Maybe you are trying to measure something outside the lab, then all of a sudden you have a strong wind that destroys your arrangement. So we call it disturbance. Or maybe a very strong vibration, something like that. So there are things that they are undesirable and you cannot avoid them. So when you are designing your control system, you must take care of these. So you give it an allowance of plus or minus an error. Then controller controls the plant or the process. We have a block diagram representation of a control system. So in this case, there are two categories. We have the open loop, just as the name says, it is open. Remember, we have our disturbance. So this is our input command. We have our controller. This is the simplest. Then we have our process. So the disturbance can come and interfere with our process. And we have our controlled output. Then we have a control system with a feedback. Now this is where the feedback is necessary. Because remember here there's a disturbance which will definitely interfere with the process. Okay? So when we don't rectify these, this error will continue going to the output and we will definitely get a distorted output. So the work of this sensor is to compare the output and the input. If the actual output is different from the expected or the set point, then it is the work of this sensor to give back the signal so that the controller can do more action. So in other words, this is also called, we can also say it is an automatic because of this feedback loop. So we are going to look at the examples of control systems and their elements. I'll start with the simplest, which is just lighting a room. Take, for example, the room we are working on. We have our switch. When you go inside the room, first of all, when it is dark, you put on the switch, then the bulb will come on to light the room. So you'll get your actual light. So here, plant is our room. The input is the desired luminosity. That is the luminescence that you will see. Then output is the actual luminosity. Subsystems here include the switch and the bulb, because if you don't, if these and these don't communicate, you will not light the room. So these are the subsystems. So you put on the light, then the bulb will come on. Or when getting out, you switch off the light, then the bulb will come off and the room will be dark. So now actuator is our bulb. Another example is the elevator. This is a bit complicated. I'll just give an example to make it light. Maybe we'll see it in the next slides how it operates. Now, when you go in an elevator, then you press the third button. But before you press the third button, you have to show the elevator that you are somewhere down there or you are somewhere up, so that it comes and open. So we'll see it in the subsequent slides. But just an example to see how the control system of the elevator is. When the third floor button is pressed on the ground floor, the elevator rises to the third floor with the speed and floor leveling accuracy. Now, assuming your elevator is stopping at third floor, but there's a mismatch between the leveling of the floor and where the elevator stands. So you'll either fall or you'll knock yourself. You'll try to lift your leg as you try to climb. So this leveling accuracy is also very important, so that it's on the same level. Or if it's not on the same level, then there is a very small difference that cannot cause a problem. So the leveling accuracy designed for passengers' comfort. So you should also be comfortable when you are moving out or you are moving in. Assuming there's a big difference of like 30 centimeters when you are trying to get inside, it will not be safe for you. So it needs several parts to be cooperative in operation to transport passengers to different floors safely and rapidly. So you find that in some elevators or lift, they go very slowly. Others go very fast until you find you have some problems with your maybe heart, something like that. So it should be very comfortable. Even the lighting system, the ventilation, all that, they should be comfortable, so that when somebody enters in, you just feel as if it is normal. So a lift subsystem includes, we have the driving, door opening, control, safety, lighting, ventilation, and security. All that, if they are not designed in a proper way, you'll find the passengers will not be comfortable. They'll prefer using the stairs, which is also healthy, but they'll take a lot of time depending on the urgency of the matter. So this is an example of how the input is the third floor, then the elevator system, all these operates or they communicate so that we get the output response as reaching the third floor, plus or minus error. So still on the elevator, we see each subsystem is an independent system that includes input, process, and output. So these are all the subsystems you can see. We have the driving system, lighting system, the door opening and door closing, because you will not be comfortable when you are going up in an elevator and the door is open. So there must be also door closing. Security system, in case of a problem, you press ABCDs, the directions are given. Then there's the control system, ventilation, safety, and all that. So this one is just a response. You find this is the error which we were talking about, plus or minus error. Third floor plus or minus error. So when you have your third floor here, you have entered in and pressed your third floor. So you find the elevator moving in this response until it reaches here. So this error is the floor leveling and all that. So when it reaches here, it stops. It is now stable because the vibrations and all the oscillations shall have stopped. So we have this as the response of the elevator, then it comes stable depending on the time. I've given the complicated and the simple control systems. Now let us see why we need the control system. One, we need the control system for power amplification or gain. For example, when you're positioning a large radar antenna by low power rotation of a knob, you're just trying to move an antenna, but you're just pressing a knob so that the knob can do that work instead of doing a lot of tedious work. So that is the power amplification or gain. Then remote control, that is the robotic arm. Example is you can use a robotic arm to pick up radioactive materials. So instead of using the physical hands, which is not advisable in radioactive materials, you can use a robotic arm to collect that remotely. Then you have an example of convenience of input form. For example, changing room temperature by a thermostat position. When you are trying to regulate the temperature of a room, you just position the thermostat to whatever temperature you want, then it will control up to that temperature you want. Then the compensation of the disturbance, this one I've discussed. For example, when you want to control an antenna position in the presence of large wind disturbance. So you find that instead of just going there to control it manually or position the antenna manually, you use the control system to compensate for that disturbance. Then you can also compare the work of the control system with the human elements in a control system. Now we can say that a human person can require a minimum of 0.3 seconds to complete one operation. Now this is just an operation maybe which was done, and it was found that a study which was done, and it was found that for it to complete one operation, we need 0.3 seconds for a human being to use it, to complete it. Now for a control system, it takes much smaller time when you use an automatic control system. For example, if you want to aim a fast moving jet plane with a gun. So when you use a control system, you will aim it very accurately. Then you can also say that human bodies cannot supervise and perform operation indefinitely. Indefinitely here means from morning to evening, evening to morning. Again, you're just in one work, supervising or performing that operation. But because you cannot withstand the human fatigue. But when you're using the control element, it will do that continuously. And it is mostly used in thermal power stations. We find when you use the human element in these thermal power stations, there's a lot of inefficiency. So when we use control systems, we find the efficiency is increased. Then the human element cannot withstand extreme conditions, either radioactive conditions, and that is why we can use an example of a robotic arm to pick up radioactive materials, or maybe in very hot environments where human elements cannot be applied. You cannot withstand that. So we use the control systems. Then we can also say that human elements cannot be standardized. For example, when you are working in the industries that they need very fine measurements or very small measurements or very accurate measurements, like the pharmaceutical industries, you find that human errors are many, but when they use the automatic controls, they can get their standard measurements. For example, in a steel industry, to make steel bars with specific diameters, you can find that it is easier for a human element to make an error. Then definitely automatic controls are cheaper and reliable as to manual systems. They are cheaper in that humans are affected by the cost of living. So when the cost of living goes up, you'll find your employees starting to make some noise that they want to go on strike, they want their pay to be increased and all that. So, and you find when you have a control system, maybe you'll not need many employees. So except servicing, a bit of servicing and all that, which is necessary for the control system. And human elements are usually affected by the cost of living. So you'll have a lot of strikes and all that. So it is wise or advisable to replace with the automatic controls. Now when you come to the classification of control systems, these control systems are divided as they go downwards. We have the natural and the man-made. Natural, here we can take on how the sun moves. That is a natural phenomena. We don't control that. And we have the man-made. So we are so much concerned with the man-made because this is where we have our controls. We can apply our controls. Man-made, we have the manual and the automatic. Then under automatic, we have the open loop and closed loop. Open loop, we have linear and non-linear. Closed loop, we also have non-linear and linear. Then we have time variant and time invariant. So those one will explain as we move. So I've just explained from the previous slide. So this one I've just given the examples from the previous slides. When you have the natural control systems like the universe or the human body, those ones are taken naturally by our creator. We don't have control over that. Then man-made control systems, we have the vehicles and the aeroplanes. We can easily make them and control them. Then in manual control systems, we can control or regulate our room temperature. We can also regulate electric fan, water level control and all that. Those are manual control systems. Then when you come to the automatic control systems, it can be the same room temperature regulation, but this one is using an SC. This one is using an electric fan. Electric fan is an example of an open loop whereby it will not know whether the temperature you need has been achieved. So it will continue pumping air so long as it is on. But in via AC, you set the temperature. So when it reaches there, it cuts off. Then we have the human body temperature control. So this one is whereby when it is hot, you start sweating and all that. So that is an automatic control. So when you start sweating, maybe you had some heavy, you had put on some heavy clothing. So it is the sweating will tell you to remove them or not. Then we have open loop control systems like the washing machines, toaster, electric fan, traffic control, and electric hand dryer. Now the open loop control systems are almost the same or closer to manual control systems, And the closed loop control systems are almost closer to automatic control systems. So here we have the refrigerator, autopilot system, and driverless cars. So you find they are interrelated. You find that we can have a regulation via electric fan, and here we have also the electric fan. So they are almost the same depending on how you are trying to use it. And the closed loop, it is like automatic. You do not require an operator to switch on or off. It will automatically regulate itself. Now, when we talk of the open loop control systems, here we say that the control action is totally independent of the output of the system. So it doesn't consider whatever is output. So if we have, this is our control systems, this is our input and our output, you find that in open loop control systems, whatever comes out is none of its business. Whether it is good or bad, it depends on the operator to judge. That is the work of the open loop system. So after controlling, whatever comes out is the work of the operator to judge whether it is okay or not. And in this, most of these industries, you find they have quality checkers to check on the product that comes out so that they can advise the operator on what to do. Then the output is not compared with the reference input. As a result, the accuracy of the system depends on calibration. Calibration is just a matter of comparing the unknown from the known. So if this one has an error, it is not well calibrated, then definitely the same error will be found at the output. So that is what I mean by saying that the output, the open loop control system depends on the calibration. The accuracy depends on the calibration. And in the presence of disturbances, it will not perform the desired task. I'd explained that. And can only be used if the relationship between the input and output is known, and if there are neither internal or external disturbances. So this one is the block diagram. I'd explained about it, whereby we have our input transducer, controller, then all of a sudden a disturbance occurs. The same process will continue with the same disturbances. So that is the disadvantage of the open loop control system. For example, we have a bread toaster. Now this machine, it operates on the preset times, in that when you set it to be 5 minutes and you're trying to toast some bread, so whether the bread turns dark or it is not toasted, it is none of the control's business. It is the work of now the operator to check whether the bread is toasted or not, so that you either add or reduce. Supposing the 5 minutes was too much for the bread to be toasted, you'll come up, the output will be a dark toasted bread or something which is burnt. So I've said the quality of toast depends upon the time for which the toast is heated. And depending on the time setting, bread is simply heated in this system and the toast quality is to be judged by the user. So that is what I've said. And so you have your desired time or the preset time. Then there's a relay which acts as the controller. Then the heating process begins. So that relay is like the timer and the controller. So when the 5 minutes expires, you'll find the machine coming off automatically with your actual toast. Then we also have another example of the traffic signal. This is what we have encountered several times. And apart from the traffic signal system, you find in some counties they have traffic controllers, or they control it now manually because of the traffic signal system. It depends on the time. So it will not judge the road that is overcrowded or the road which is having a lot of jam so that it can open. It will operate on the time. If it is 5 minutes on one particular road, it will turn to the other 5 minutes on that. So it will not depend on which road is congested or not. So it will have also depend on the desired time and the actual traffic control. Here it will show by using the lights, the red, yellow, and all that, so that the traffic can move or not. Then we have the second class, that is the closed loop control system. And in this case, the control action depends on the output. So that one is now having a feedback. So it depends on the output. So it has a feedback, and it is this feedback which will do the comparison between the input and the output. It makes the control system robust to uncertainty and disturbances. By this I mean, if there's a disturbance somewhere here, it is the work of this feedback to know that whatever is coming out is not favorable, and then takes back the feedback to the controller so that more control action can be done. It is always equipped with a sensor which is used to monitor the output and compare with the expected results. Now this feedback is the sensor. So all those are explained in that particular slide, what happens. And the components or the elements, we have the comparison element, control element, correction element, process or plant element, and the measurement element. Now because of the feedback, because the feedback does the comparison, so we'll have these as the comparison element, and then the correction element. So you can see from the diagram here, we have our reference transducer. You put in a command to a transducer. Then we get our error, which is the comparison between the output and the input. Remember, this is the input now to the controller. So first of all, it is compared, then it is controlled, then it goes to the process to be controlled and all that. So we have the forward path and the feedback path. Another name for feedback path is the feedback loop. So when this one is not there, the feedback loop is not there, we'll definitely have an open loop. So this is just a modification of an open loop to cater for any disturbances or any error. So as we had said, this is the reference point, that is the RT. This is the reference point from the transducer. Then we have our error, which is now put into a controller. Then we have our control signal as the CT. This is our output controller. So in other cases, you can find the controller and the process being as one. Then you have the manipulated variable that is here at the MT from the controller. Then from the feedback signal, we have the BT. That is the signal that is used for the comparison. There are different categories or types of closed loop systems. For example, we can have a single input, single output system. In this system, we have one input and we have one output. So this one is very simple. It has a single input and it has a single output. Then we also have multi-loop feedback systems. So here, for example, we have the inner loop and the outer loop. So they have different sensors depending on whatever you are trying to measure. So you can have maybe sensor for temperature, sensor for pressure, sensor for ABCDs, depending on whatever you are measuring, so that you have an actual output. So these sensors, they are variables that interfere with the actual output. So they are measured or taken back for further control action. Then another type is multivariable control systems. So in this case, we have several inputs having several outputs with several sensors depending on your particular system. Others can be very much complicated. Then we have multi-input, multi-output. So we have several input, several outputs. Then we have different measurements or feedback. So I'll give examples. For example, one air conditioner system. This is a closed loop system. So you find that you set it here. This is the desired temperature. You set whatever temperature you want. Then now it is the work of the thermistor to compare whether the room has reached the temperature you want. If it is not attained, you find it either giving the feedback back to the controller to pump in more heat or cold water so that you can attain that temperature that you want. Then another system is also the home heating, which is almost the same, but now it acts on the opposite of heating the room. So you find the right temperature, the house temperature. Then you have your temperature sensor there. You have your desired temperature. It's almost the same as the first one. Then you also have the manual speed control system. For example, when you are driving a train and all that. So this is how you check. First of all, when you only want to check on the speed. First of all, there's this sensor or the eyes that tell you to check on the speedometer. When it is high or low, the brain is now the control action, and now the hands is the actuator, which will either decelerate or do whatever is necessary so that you can obtain the actual speed. Then we also have another example of a boiler. In boiler, it's a bit complicated because you have several inputs and you have output. This is just the generation. You are trying to feed in some water. You feed in fuel. Then there's the valve for air. You also feed in air. Now, depending on whatever is here, the output will have to get the steam as the output, which is directly connected to the turbine. The turbine is connected to the generator through a shaft. So when the steam is obtained, it is used directly to generate electricity. However, there are some checkings that need to be done on this steam temperature. We have to check the temperature. We have to check the oxygen here. We also have to check the pressure. And then you do the comparison. If it is the one which is necessary, then you proceed. When you find one or two is not on the right quantity or quality which is necessary, then it is the work of this comparator to give a signal to for a control action, like maybe to open the valve for fuel or water and all that. So that is where we find multi-inputs with a single output. Another example is also for a human being. For example, a very simple one, when something falls down from the table, it is your eyes that will see that it has fallen. Then your brain will tell your hands to go and collect it. So you'll have to manipulate your hands until it reaches the desired position of to collect the book. So I've just saying position of the book is given as the reference where the book has fallen, or maybe the book is somewhere on the table. So feedback signal from eyes compares the actual position of hands with the reference position. Then the error signal is given to the brain. So the brain will see how far your hands can go to collect that book, and you'll have it. So that is another example. So here is just a comparison, whatever I've said, between the open loop and closed loop. It is, most importantly, the open loop is not accurate as compared to the closed loop. And this is closed loop is very continuous. As we can see, the open loop is not very much continuous. There's no feedback loop and all that. So you find the control loop, closed loop control system is mostly preferred. However, it is also very expensive and complicated to design as compared to the open loop control systems. There are also requirements of an ideal control system. First of all, it must be accurate, it must be sensitive, it must be stable, and the bandwidth should be the one which is satisfactory output, the speed, and the oscillations. Now, oscillations is what we term as the response, because you find some control systems, they take a lot of time to stabilize. So it should not take that much time to stabilize. It should go and stabilize immediately, or it takes very short time to stabilize. Now, at the beginning of this course, you are expected to design, and this is the process that will take in designing a control system. First of all, you establish the control goals, what you want to achieve. Then you identify the variables to that control system. The variables can include temperature, pressure, all that. Then you write the specification for each of the variables. The specifications means the minimum and maximum specifications or quantities of these variables. Then you establish the system configuration and identify the actuator, that is the control action. Obtain a model of the process, the actuator, and the sensor. So you also have to identify all these. If you are, depending on the variables, what sensors do you want? Do you need? Then you describe a controller and select key parameters to be adjusted, because you find that these parameters, they are interconnected. When you adjust one, the other one will also be affected. So you have to study the relationship. Then now you optimize. You optimize meanings you try to obtain the maximum value or the maximum output which is recommended. Then if the parameter meets the specification, then finalize your design. If it doesn't, you go back to step 4, you establish the system configuration and identify the actuator. So maybe assignments, I only dwelt on so much on the closed loop and the open loop. So maybe you can read further and see the linear and nonlinear, continuous and discrete. And I think that is the end of lesson 1. Thank you.
These televised lectures supplement our robust online learning going on our MKU online platform. You can view more on our televised lectures via our online platform. We are in a digital era, and Mount Kenya University knows this. The following are the steps to follow so as to complete your online application. Download the application form from the website www.mku.ac.ke. Attach copies of your academic certificates and ID. Pay the application fees via M-Pesa pay bill number 270988. Your ID is the account number. 2,000 shillings is the charge for a postgraduate. You can also deposit in the bank accounts provided on the website. Then, email all the above to apply@mku.ac.ke.